Hi guys, welcome to my channel and welcome to another new live demo. So in this demo I'm trying to take some measurements for the frequency response of the FIR filter I shared with you, I designed and I shared with you last week. My setup for this frequency response test, I have an FPGA Spartan-7. Within the FPGA I have a DDS that does a frequency sweep from 100 Hz all the way to 40 kHz, and each frequency has a dwell time of 10 milliseconds, meaning each frequency lasts 10 milliseconds. And the output of the DDS, it goes to an FIR, the FIR we designed last time together, and the digital output of the FIR goes to a development board, a DAC development board, and then the output comes to my oscilloscope right here, and another output goes to the spectrum analyzer that I will share with you later. So let's look at the time domain. So time domain, you see here there's a pattern of sweeps, so each sweep takes about 4 seconds, so let's confirm that. So pretty much like this. So with a cursor, so right here, so roughly 4 seconds. The interesting thing also to notice here is that at some point during the sweep the frequencies start to roll down. So right here, so like after 1.3 seconds the frequency starts to lose their power strength and start to get attenuated more and more till you see nothing. So pretty much after, let's say half the time, after 2 seconds, and this is roughly here like around 20 kHz, basically you see nothing. So from 20 kHz all the way to 40 kHz, all the signals are completely suppressed, completely attenuated. So this is our measurements here in time domain. So this is how it looks like again, and then I will move to the spectrum analyzer and share with you guys the measurements I took in the spectrum analyzer. Okay, the spectrum analyzer now. The spectrum analyzer I'm using right here is unfortunately it cannot go lower than 9 kHz. That's why my sweep over here, it goes from 9 kHz all the way to 40 kHz. So you can see, first of all, my gain is supposed to be 3 dB, you can see that on the top, and the cutoff frequency here is 0 dB. So around 0 dB I don't have 12.5 kHz as I expected. I have 14.7 or 14.5, let's say, kilohertz if it's supposed to be 0 dB. So that's another thing, like not always the simulation results matches the real life measurements, right? So if you really need to get like 12.5 as I expected, then we need to go back and tweak the coefficients again and the measurements again. But the good news is that I was able to find that the rejection, the amount of rejection I wanted was met, was successfully realized. So I can show you that. So I expected 60 dB at 20 kHz, and I was able to get that. So here we have minus 57, but because of the 3 dB down, so with the offset, so it's minus 60, and I have 20.2 kHz. That's pretty much a good measurement actually. So that's pretty good. So the other thing I want to share with you, since everything is connected together, I just want to share with you my ILA on the FPGA. So we'll run the ILA and look at the same time at the inputs and the output of the filter, how they look like. Let's take a look. So this is my ILA. So I'm gonna run it again. Now it stopped, but just trigger. So this must be a low frequency, that's why. So this is a high frequency, basically you see nothing coming out of the RF out. So we try again. So same thing. I keep repeating until I hit a low frequency, just for fun. Anyway, so this is kind of sort of a low frequency, but it's not. So the two other signals you can see, the important one is the FIR sample valid in, and as I told you guys, that valid in is only high for one FIR clock cycle, which is 5 nanoseconds, and the other signal, the chip selected just for my DAC. That's pretty much it. I'm really excited that I shared this demo with you, and I hope you guys learned something from it. And if you guys like it, please hit a like on my channel and subscribe, and stay in touch. Another new video is coming up next week, and it's going to be about how to design a 2-channel FIR filter. Thank you, and another day. Bye-bye.